Next topic is torque on electric dipole when it is placed in external electric field. Right? We shall study the different sort of behaviors of electric dipole when placed in different sort of either electric or magnetic field and so forth. Now consider we have an electric field. This electric field is uniform. Uniform means the value of electric field at every point of this particular region will be equal and same. If it is 10 over here, then it will be 10 over here. At every point, electric field will have a magnitude of 10 Newton per coulomb. So this is the electric field. Okay. Now imagine an electric dipole is placed in this electric field such that the dipole is oriented in this way. Right? This is minus q and that is plus q, and its length is twice a. So the dipole moves, but remember first, the external electric field will apply some force on these two charges separately. Force on this positive charge will be along the field as well. That is, a force acts on this F plus, and this will be equal to the charge multiplied by the electric field. Force on the negative charge is equal to F minus is equal to again Q. Both have same magnitude but pointing in different directions. So what will be the net force on the electric dipole? Net force F is equal to, this will be minus Q and that will be plus Q. The net force is equal to vectorially F due to plus F due to negative charge, and vectorially they are minus of QE plus of QE equals to 0. That is, the net force on any electric dipole is always 0 if it is placed in an uniform electric field. Remember, the field is uniform. Uniform means, as I told earlier. Now, the forces being equal, opposite cancel each other. Now, what happens to the dipole when this is placed in the external electric field in such a orientation or any orientation? Now, imagine this angle is theta. Means we are going to study the behavior of the dipole in this electric field. Okay, now what happens? These two different forces try to rotate the dipole either clockwise or anti-clockwise. To rotate any body, we must have what? A torque. And how much that torque will be, we shall be doing the mathematics for that. Now, these two forces, QE and minus QE, are equal but in opposite direction as well. That's we had proved earlier. But the most important thing is that these two forces are not acting on the system along the same line. So they will produce some different sort of effect, and that effect will try to rotate or turn the dipole about its center of mass or in the electric field. Remember, the two forces being equal are not acting in the same line. That's why they produce a turning effect called torque. So how shall we find that value of torque? And torque is equal to what? Either of the force multiplied by the perpendicular distance between the two forces. Now, what will be the perpendicular distance between the two forces? Now, torque tau is equal to either of the force multiplied by the perpendicular distance. We had studied in class 11 this in detail. Now, what is the perpendicular distance? From the figure, let's calculate this. Complete this triangle. Obviously, the two forces are separated from each other perpendicularly by a distance of this much. If this is A, that is B, and that is C, then the perpendicular distance between the two forces is what? This is BC, because force F1 goes this way and F2 goes this way. This is the perpendicular distance. So BC will be the perpendicular distance. So I must write F into BC, and F equals to what? Either of the forces, that is Q into E into what is BC? From, if this is theta, this must be again theta, and the hypotenuse is 2a. Take sine theta is equal to what? BC over AB, so that BC equal to AB sine theta, and AB equals to what? Twice of A, that is twice of A sine theta. So we got the perpendicular distance is equal to twice of A and sine of theta. Now that is twice A sine theta. But now we can have different manipulation over here. This Q multiplied by 2A, that is twice AQ is equal to the dipole moment. So this is twice AQ E and sine theta, and this is equals to P dipole moment P E sine theta, that is torque equal to P E sine theta. Now this is the magnitude of the torque acting on this electric dipole when placed in the external but uniform electric field. This E has a uniform value, it cannot be variable. Now in vector form we can write this: tau is equal to P cross E. So this takes in what? Sine theta, because A cross B equals to AB sine theta. So P plays the role of A and E plays the role of B. Right? It means the torque on the system depends on the three values, that is P, E and sine theta. But P of the system is fixed, electric field is uniform. So more specifically, the dipole moment depends on sine theta or rather than theta, that is tau is directly proportional to theta. If we change the value of theta, we get different values of dipole. Now see the cases. Case number 1, when theta equals to 0. Theta equals to 0 means, imagine the dipole moment will be where? It will be pointing towards minus q to plus q. It means this is the dipole moment P vector. Now I am showing this by this marker, that is minus to plus. Okay. If theta equals to 0, then dipole moment will be parallel to the electric field. Means this black line or this marker is oriented this way. This will be the position. So in that case, imagine the two forces will be acting on the dipole along the same line. It means if two forces being equal and opposite acting along the same line, they must cancel out their effects. So there will be no torque on the dipole. Let's do it mathematically. Tau is equal to P E sine of 0. Sine 0 means 0. So tau is equal to 0. When no torque on the system acts, and this position is physically named as stable equilibrium. Stable equilibrium. Stable means net force of the system is 0. That's already been proved. Now equilibrium means it has no further movement if it is displaced from the that particular position. Imagine the dipole was placed like this, and if you disturb a little bit by any small angle, it will fluctuate like this, but finally it gets stabilized. It means net force of the dipole will be 0, so the stability is formed, and equilibrium means it finally comes back to the original position if disturbed. So this angle or orientation indicates to stable equilibrium. Remember, this is most frequently asked in board exams. Now case number 2, when theta is equals to 180, then sine 180 equals to again 0. It means tau will be equal to 0. Now what happens? The dipole will be aligning this way. This way. The dipole will be aligning this way, means opposite to the electric field. Again, there will be no torque, but this corresponds to unstable equilibrium. Unstable equilibrium. Unstable means if you disturb the dipole in this angle, if it is already there, and if you disturb it, then it will not come back to its original orientation or position. But in this case, if you had disturbed when it was at 0 degree, it will again come back to the same position, but it does not. That's why the names are unstable equilibrium and it is stable equilibrium. One more case is left, that is if theta equals to 90 degree. If theta equals to 90 degree, then we know sine 90 equals to 1, and that is the maximum value. It means tau will be P into E, or it is the maximum torque. So at this position or 90 degree, that is when the dipole is perpendicular, either this way or this way, downward, it will be experiencing a maximum torque over itself. Okay, so these are the 3 cases. Remember, this is very important. This is very important. Not this is, sometime we'll do in mathematics, but this is all about the experience of a dipole when placed in external electric field. Okay, now these are the 3 cases.